So first I would like to thank you your presence here. I'm honored to manage this geometry session here in the 30 Colóquio da Sociedade Brasileira. I would like to thank all the speakers for coming to this colloquio. It's a pleasure for me that you all have accepted the invitation. And I hope that you all have a really good week here in Rio de Janeiro. So first, we are going to start with a good friend of mine, Rosenberg, that I think he doesn't need any presentation. But I have to do it. He probably is one of the finest geometry in the world.
Oh, no.
He doesn't see so, but I do. So, well, today he's going to start the colloquio with a talk entitled Area Estimate for Minimal Surface in Hyperbolic 3 Manifold. So, thank you.
Well, thank you. I hope it's okay that I speak English, but if you don't understand any English, you could say so and I'll try and speak Portuguese. Maybe that'll help. So, as Jose said, I'll be talking about area estimates for minimal surfaces in hyperbolic 3 manifolds. And what I'd like to do today is show you that there are results in topology and geometry in n-dimensional manifolds, especially dimension 3, that come together to give the area estimates I'm going to talk about. So I sort of like to explain the ideas that go behind how one gets these estimates. So the notation I'd like to use throughout the talk, I'll always note n a 3-dimensional hyperbolic manifold that's complete and finite volume. And I'll note the volume of a manifold by volume n. I'll also assume all the ambient manifolds are always orientable. Whenever I write an ambient manifold, so ambient manifolds are orientable. This won't be the case for surfaces in these manifolds. When I say a surface in the manifold, you should think of it as being orientable or non-orientable. These manifolds n that I'll be talking about have no boundary. They may be closed manifolds, may be compact without boundary. If they're not compact without boundary, then they have a finite number of cusp ends. And I'll say just 2 words now about the geometry of these cusp ends. Each cusp end is foliated by what I would call Haro tori. I'll parameterize these tori going from t of 1/2 to t of s, where this will be distance from the torus t of 1/2. Now, when I say this is a Haro torus, it's the quotient of a horosphere of hyperbolic space by 2 independent parabolic isometries. So it's an honest-to-goodness torus. It has mean curvature 1 pointing towards the cusp. All of these tori have mean curvature 1, and they're concave with respect to this part of n. Okay, then this is not a mean convex manifold when I cut off the cusp. And the diameter of t of s goes down exponentially with s. So it's e to the minus s, the diameter of t of 1. So as you go a distance s along these geodesics, you're shrinking down size exponentially in s. That's the geometry of these cusp ends of the manifolds I'm talking about. So the theorem that I'd like to give the ideas today is a theorem that I proved with Laurent Mazet. And it's really contained in several papers that are on archive. But for these manifolds n, the applications of this work is the following. So n is as above. If the Hagar genus of this n is at least 7, then any closed embedded minimal surface in N has area greater than or equal to 2 pi if it's orientable, and area greater than or equal to pi if it's non-orientable. I'll explain to you in a few moments what the Hegat genus is of a manifold. It's a topological notion. It's not geometrical. And this Hegat genus will always be denoted G Hegat of N, the Hegat genus of N. We'll see what that is shortly. But let me mention that there are an infinite number of manifolds that have Hegat genus large. There's a theorem of Suto that if one takes M2, a closed orientable surface of genus at least 1, so suppose I note the genus by G, and if F is an anisotropy diffeomorphism of the surface to itself, then the mapping cylinder of F, that is the manifold N equals M cross 0, 1, where identify F to the M of x1 with x0. So this, I'm quotienting this manifold M cross 1 with M cross 0 by the diffeomorphism F to the M. So let me just, I left out a point here. I have this anisotropy diffeomorphism. Then there exists an N, an integer N, such that if M is at least N, for all integers M greater than or equal to N, when one looks at this mapping torus here, this has a hyperbolic structure. That's why I called it N. But what's interesting is its Hegat genus is at least 2n plus 1. And the Hegat genus of this N is greater than or equal to its 2n plus 1. So as soon as you take a surface of genus 3, you have Hegat genus at least 7 for any anisotropy diffeomorphism on that surface, and you take the suspension. So there's an infinite number of such manifolds that are hyperbolic. Even here, it's compact without boundary of Hegat genus at least 7. Okay, let me mention some of the topology that goes into what we're going to use for some remarks on topology. What is the Hegat genus of a manifold? What is a compression body? The definition, in three-dimensional topology, one has this notion of a compression body. You start with a closed orientable surface M2. M2 is a closed orientable surface. You take M2 cross 0, 1, the product, and to M2 cross 1, you attach handles that are 2 handles and 3 handles with 2 handles and 3 handles attached to M2 cross 1. That's a compression body. Definition of a compression body. Start off with some closed manifold without boundary. Take the Cartesian product with 0, 1. And to M2 cross 1, attach a 2 handle and a 3 handle. Let me give you an example to illustrate that. Let's take M2 to be a 2 torus. And let's begin by taking a 2 handle attached to M2 cross 1. So what is a 2 handle attached to a torus, M2 cross 1? There's a torus. Attach a 2 handle. You take a 2 disk. You take a map of its boundary to M2 cross 1. So here I'll map the boundary to this generated fundamental group. You attach the 2 disk. And then you thicken the 2 disk. So I'll draw it like this. This is 2 disk thickened. I'll imagine that. Okay. That's M2 cross 1, T2 cross 1, with a 2 disk attached. It's a thickened 2 disk. This new manifold, if you think about it, has boundary that's a 2 sphere. That's a little topology. Draw some pictures to see that the boundary of this new manifold, T2 cross 1, with this 2 handle attached to the 2 sphere. To this 2 sphere, I can attach a 3 handle. What is a 3 handle? A 3 handle is a ball of dimension 3 attached by its boundary, which is a sphere. So I take a ball, I'll attach the boundary to this boundary 2 sphere here. And now it's a nice exercise in topology to see that what you got was a solid torus. A sphere with a handle of index 1 attached, a handle body. So the end of this definition here of a compression body is a handle body is a compression body whose boundary is equal to only M2 cross 0. So I attach 2 handles and 3 handles to M2 cross 1, but I do so that this only boundary is left is M2 cross 0. If you think about it, that's the same thing as taking a ball and attaching 1 handles. That's a one handle. So I thicken this and I get two handles. So this is a ball with these 2 1 handles attached. That's a solid pretzel. It's a genus 2 surface. And it's the inside of this. So a handle body is simply an orientable surface of a certain genus, here genus 2, and you put it in R3 in the standard way. So you only attached 1 handles to a solid ball. The Haygaard genus, okay, so what is a Haygaard surface? Let me finish now the definition of Haygaard genus. Definition, sigma 2 in M3 is a Haygaard surface, if sigma separates M3 into 2 components, each of which is a compression body. 2 compression bodies. For example, 2 handle bodies. The smallest genus of such a surface, the smallest genus of such a sigma in M3 is called the Haygaard genus of M3. So the Haygaard genus of this 3 manifold is equal to the smallest genus of such a sigma. For example, for the 3 sphere, the Haygaard genus of the 3 sphere is 0, because I can take 2 balls and identify them along their boundary. So the Haygaard surface is a 2 sphere which has genus 0. You can't get lower than 0. The Haygaard genus of S2 cross S1 is 1, I can write S2 cross S1 as two solid torus identified along the boundary, which is a torus, which is genus 1. And I certainly can't do that for two balls. I can't identify two balls along the boundary to get S2 cross S1. So this is a topological notion, the Heegaard genus of a three-manifold, and that's the topology that I'll need. Okay. Now, a geometric theorem proved by Meeks, Simon, and Yao, which says when a three-manifold is indeed a handle body in terms of area of surfaces. So this is a theorem Meeks, Leon, Simon, and Yao says the following. Take any Riemannian three-manifold, orientable compact, now it's Riemannian, whose boundary is connected and not empty. And consider the infimum of all surfaces sigma in M3, such as sigma is isotopic, well, consider the infimum of the area of all surfaces sigma in M3. Sigma is isotopic to the boundary of M. Okay? So look at the area of all surfaces sigma in M isotopic to the boundary. There are two possibilities. Maybe this infimum is 0, or maybe it's positive. If it's 0, then the theorem says M3 is a handle body. So it's really a solid pretzel. If M, the boundary here is of genus 6, then you see a three-dimensional ball with 6 one-dimensional handles attached. A solid pretzel with 6 holes in it. The other possibility is if this infimum, I won't write the whole thing, just of this, is greater than 0, then indeed you can find inside M an embedded minimal surface that's stable and has area at most the area of the boundary of M. Then there exists a stable minimal surface embedded in M, and its area is at most the area of the boundary of M. Okay, I think that is all I'll need as concerning theorems. Let me just check that I'm... Okay, so now let's talk about area of minimal surfaces in hyperbolic three-manifolds using these theorems and these ideas. So suppose sigma is an embedded, orientable, minimal surface in this hyperbolic three-manifold N3, complete in the finite volume. So sigma has a certain genus, G sigma, and if you consider the Gauss equation and the Gauss-Bonnet formula, then it's easy to see that an upper bound for the area of sigma, even at not assuming embedded, just immersed, is less than or equal to 2 pi times the absolute value of the Euler characteristic of sigma. So this is 2 pi 2 G sigma minus 2. That follows from the Gauss equation and the Gauss-Bonnet formula. I won't do that calculation. It's an easy calculation. In particular, you see that if you have an immersed compact minimal surface that's orientable in a hyperbolic three-manifold, this genus has to be at least 2. Because if it's strictly less than 2, this number is negative or 0, but you have to have positive area, so it's impossible. So in particular, the genus is always greater than or equal to 2. You can't have a minimal torus or a two-sphere in a hyperbolic three-manifold. Now we're interested in lower bounds for the area of sigma. So this is always true, independently of the sigma and the hyperbolic three-manifold. What really interests us is to see if you can have lower bounds. For example, if you think about geodesics and hyperbolic surfaces, you can easily construct examples of compact orientable hyperbolic surfaces where the length of geodesics is as small as you want, embedded geodesics. So there is no lower bound for the length of geodesics on hyperbolic surfaces. But strangely enough, there's always a definite positive lower bound for the area of a minimal surface in a hyperbolic three-manifold, which is true for all hyperbolic three-manifolds. What I'm interested in is getting the best lower bound. Okay, so if sigma is stable, so any small infinitesimal variation of sigma has area, at least the area of sigma, then, in fact, one has pi times the absolute value of the Euler characteristic of sigma is less than or equal to the area of sigma. So since this is always greater than or equal to 2 pi, because it's pi times 2g sigma minus 2, g sigma is at least 2, you see that, in particular, the area of sigma is greater than or equal to 2 pi when it's stable. Now, why is this true? The stability inequality for stable minimal surfaces says that the integral of the second fundamental form of sigma squared plus the Ricci curvature of the normal vector to sigma times, well, I should put another term in here. I'll do it this way. Times 1 is less than or equal to 0. Because the stability inequality in general is the following, which I'm applying to the function 1. It says that for all f, we can even take it just C2 on sigma. Sigma is compact, so I don't have to worry about the support being compact. One has the integral of L of f over sigma less than or equal to 0, where L is Laplacian plus norm a squared plus Ricci of the normal. That's the stability inequality for minimal surfaces that are stable. So if we apply this to f equals 1 and you use change of variables, you get this inequality. Now if you put in the Gauss equation, because norm of a squared is minus twice the extrinsic curvature of sigma, and this is equal to the intrinsic curvature plus 1. And if you put Gauss-Bonnet formula into that, you get this inequality. So stable minimal surfaces, the area, if they're orientable, the area is at least 2 pi. What's the next kind of surface after a stable minimal surface? It's a minimal surface of index 1. So what can say about index 1 minimal surfaces and their area? So suppose sigma is index 1 orientable in this hyperbolic three-manifold N3, then one has the area of sigma is greater than or equal to 2 pi, the genus of sigma minus 2 minus the integer part of g sigma plus 1 over 2. This is the integer part of this number. This is a monotone. This quantity here is monotone non-decreasing. And it's easy to check that the first time this is greater than or equal to 1 is when the genus is greater than or equal to 6. If this is 6, you get 4 here. 6 plus 1 is 7 over 2. The integer part is 3. 4 minus 3 is 1. So after 6, this is always greater than or equal to 1. So in particular, the index of sigma is greater than or equal to 2 pi if the genus of sigma is greater than or equal to 6. Okay, so for index 1 minimal surfaces, one has an area estimate that I want in terms of the genus being at least 6. The proof of this, which I won't give because I don't think I'll have time, perhaps at the end I'll have time, but I doubt it, it's the Hersh trick. The Hersh trick. This is something that's often used in geometry. In general, it's used in positive curvature. And in positive curvature, when you use it, you get lower bounds for the area, upper bounds for the area. It turns out that when you use it in negative curvature, you get lower bounds for the area. As far as I know, this is the first time that this point of view has been taken for negative curvature. So let's assume this. So we have what we want for stable minimal surfaces. We have what we want for index 1 minimal surfaces. There's all the other minimal surfaces, index 2, 3, etc. How do you get control of their area, right? Well, there you manage to ask the following kind of question. Take an arbitrary manifold. Forget hyperbolic geometry now. Take an arbitrary manifold of arbitrary dimension, closed manifold, and try and understand what hypersurface, embedded hypersurface in that manifold, has least area possible. Maybe there is no such manifold, right? Maybe there is no such minimal hypersurface. But if there is, what can you say about it? Well, we prove the following theorem. So, theorem. Consider a manifold, orientable, closed, 2 less than or equal to n less than or equal to 6, dimension most 7, and consider looking for the a minimal hypersurface in there that's embedded and has area less than or equal to the area of any other minimal hypersurface. So define A of m to be the infimum of the area of sigma if sigma is a embedded minimal hypersurface in M that's orientable, or twice the area of sigma if sigma is an embedded minimal hypersurface in M which is non-orientable. The reason for the 2 there is that when one does this theory, non-orientable hypersurfaces always come up with multiplicity 2. So you look at this infimum, and you might ask yourself the question, well, is this infimum realized by a compact embedded minimal hypersurface? And if it is, what are the properties of this hypersurface? Well, in particular, the theorem says it's realized, and not only that, but the hypersurface that realizes it has definite nice properties. It's stable or index 1. So we can apply the theory that I've just been discussing. So the theorem says that A of m is realized and if sigma realizes A of m, then 1, 2, or 3 is true. What is 1? Sigma is orientable. I mean, O, orientable embedded minimal hypersurfaces, and U, non-orientable. Sigma is orientable. A of m is equal to the volume of sigma, and sigma is of index 1. And sigma is a minimax hypersurface. It's equal to sigma is a min-max hypersurface, and its area is equal to the Algren-Pitts width of M, Algren-Pitts width of M, width of M, corresponding to the fundamental class of M in the n plus first group of homology of M with integer coefficients. That's condition 1. So you might think of the n-dimensional sphere. You do minimax with one-dimensional sweep-outs. You get an equatorial n-1 sphere. And that equator is such a sigma, satisfying 1. It's index 1, and A of m is equal to that. So in the 3-sphere, you would get an equatorial 2-sphere whose area is 4 pi. Second possibility is sigma is orientable and stable. Okay, for us that's really great because the area is at least 2 pi in hyperbolic 3 manifolds. Third possibility is sigma is non-orientable and stable. This is non-orientable embedded minimal hypersurfaces. For example, it might be a projective plane in projective 3 space, which is in this case, one has much more information than the oriented two-sheeted covering of sigma, called sigma tilde, has index 0 or 1. Has index 0 or 1. If it's 1, then the width, the Algren-Pitts width of M is equal to the area of sigma tilde, which is twice the area of sigma. Okay. The rest of the theorem says any embedded minimal hypersurface that realizes this number A of m satisfies 1, 2, or 3. So this characterizes those minimal hypersurfaces that have least area. But in particular, you always have a minimal hypersurface that's stable or of index 1. So getting back to our problem, at least for compact minimal hyperbolic 3 manifolds n, we see how to solve our problem. For the moment, we almost see. Because I want to show that any minimal surface has area at least 2 pi or pi when the Hagar genus is greater than or equal to 7. Well, I take a minimal surface, I might as well look at the smallest area possible of all compact minimal surfaces in n. Of course, if n is not compact, I didn't say there's such a theorem yet. So suppose n is a compact hyperbolic 3 manifold. You look at the smallest minimal surface, has smallest area. It's realized, so it exists. If it's stable, its area is at least 2 pi, and you're finished. and the other minimal surface in N has area at least 2 pi, because you took the smallest area. Suppose it's index 1. Well, if you knew that it was a Haygaard surface, if you knew this sigma separated M into 2 components and each component was a handle body, then you could say its genus was greater than or equal to the Haygaard genus. So its genus would be greater than or equal to 7. So by this theorem here, you would know the area is at least 2 pi. So there's one thing missing in that discussion. Why is an index 1 minimal surface in this closed hyperbolic 3 manifold a Haygaard surface? Well, suppose sigma has index 1 in this 3 manifold. It's an embedded minimal surface. I claim it has to separate into 2 components. If it doesn't separate, then it represents a non-zero element in the homology class of the ambient 3 manifold. You can always minimize area in homology classes. That's due to Federer. And you get a stable minimal surface of area less than or equal to what you started with in that homology class. Well, that stable surface is area at least 2 pi. So you're finished. So therefore, it's 0 in homology. So it separates into 2 components. Look at one of the components and apply this theorem here. Start minimizing area in the isotopy class of the boundary. Either you get 0, in which case it's a handle body. If you don't get 0, you get a stable surface in there of less area, which is going to be bigger than or equal to 2 pi. So in any case, you can assume that it's a handle body. So this index 1 surface separates into 2 handle bodies. Therefore, its genus is greater than or equal to the Haygaard genus. So if you suppose the Haygaard genus is at least 7, its genus is greater than or equal to 7, and you have this inequality. Of course, all that theory breaks down for the moment when N is not compact. All that discussion was for compact here. Here, this manifold here, for this theorem, is a closed manifold. So somehow or other you have to prove this theorem for non-compact hyperbolic 3 manifolds. Let's see. 5 more minutes. Okay. Okay, let me say 2 words on how you go to non-compact hyperbolic 3 manifolds for this theory. So let me just make one remark. That discussion I just made shows that in dimension 3, one gets more information about the topology of the surface that realizes A of M. In dimension 3, we showed that this min-max surface of index 1 is a Haygaard surface. So in dimension 3, you conclude that the genus of sigma is greater than or equal to the Haygaard genus of M3. That's case 1. And then in case 3, what you really get is the genus of sigma tilde, the 2-sheeted cover, is greater than or equal to the Haygaard genus of M3 minus 1. These are important estimates for 3-dimensional geometry. You get control over the genus of the surface that has least area in your 3 manifold. Okay, so let me now discuss what's going on for the non-compact hyperbolic 3 manifolds in 5 minutes or 4 minutes. So this Haygaard genus was defined for compact manifolds in terms of handle bodies. How do you do it for non-compact N3s? So here's our N with cusp ends. Let's say cusp ends. I take a cusp end. I parameterize it so the horotor starts over 1/2, T of 1. It gets really thin, T of S. I cut it off at some point. Cut it off at T of some C0 and throw this away. So you get some compact manifold N bar, compact with boundary equal tori. For each cusp end, I choose a constant. I throw away the non-compact part. It's bounded by tori. Then there's a theorem in hyperbolic geometry, R-E-I-C-K, and Sedgwick, who showed that one can do den surgery on this n bar to get a new hyperbolic manifold whose Higard genus is the same as the Higard genus of this compact manifold. One can attach solid tori to the boundary T of C0 to each one, put in a solid torus here, to get a manifold n tilde that's hyperbolic, closed, compact, no boundary, and its Higard genus is the same. The Higard genus of n is the same as the Higard genus of n tilde. There's an infinite number of ways of doing this. They call this, Thurston calls this den surgery, where you attach a solid torus to the boundary torus in such a way that you get a hyperbolic structure on the new manifolds. So this is a process that exists, and they managed to prove this theorem. Now, we have a theorem that says that if the diameter of T of 1 is small, okay, so I take this cusp end. If I lift the metric to hyperbolic space, you see the metric dx squared plus dy squared plus dz squared over z squared, z greater than or equal to 1/2. The horosphere here that has quotient T of 1/2 is z equals 1/2. That's T of 1/2. I want to make a change of metric in each cusp end where I replace this by a function c of z squared, where c of z is equal to z in 1/2 1, and c prime of z is greater than 0 for z greater than 1. Z goes to infinity. So you get a complete metric now on this, such that the geometry here is changed. For example, if I add the condition c of z goes to 2 as z goes to infinity, then the geometry is becoming sort of like Euclidean geometry as I go out. These tori now are converging. The mean curvature of these tori is given by the derivative of c prime of z. They're converging to Euclidean tori. Okay, so this is T of 1/2, T of 1. Well, Mazzei and I proved there's a maximum principle in these three manifolds in the following sense. Any compact minimal surface in such a manifold can't go into these cusps further than T of 1. All the compact embedded minimal surfaces in N are contained in the part here, T of 1, provided the initial diameter of T of 1 was sufficiently small. So I start off by going out in all the cusps to that sufficiently small number, so the tori T of S, a really small diameter. And then I applied this theorem of Mazzei and me to say that all the minimal surfaces don't go into that cusp after T of 1. They're all on this side, maybe. They don't go past T of 1. So I won't write down that theorem. I don't have time. Yeah. There's that theorem. So then you have to, so you're interested in analyzing all those minimal surfaces that didn't go far out in the cusp. Now I go out to a certain L here, T of L. Okay, so here say T of 1, T of L. Any minimal surface. So now I'm going to attach a solid torus here. And forget about the metric. I don't care about the new metric. Just attach a solid torus T of L, but keep the metric coming from C here. Don't change the metric up to T of L, but attach the solid torus. I have a closed manifold. For this closed manifold, I can look at the smallest area of a minimal surface in that closed manifold. Call that closed manifold N double bar.
Hello. You are minus...
Minus 2 minutes?
Yeah.
Okay. Minus 3 minutes, I stop. You look at all the area of all those closed surfaces, and you realize that because this is only almost Euclidean, by monotonicity, any minimal surface that intersects T of 1 will have to go all the way to T of L. So once it goes to T of L, by the monotonicity formula, it has lots of area. In particular, I can choose its area so that A1 of n, the smallest area of minimal surfaces in n, is less than A of n double bar minus 1. No, I won't have time to explain, I'm sorry. In any case, you can manage to extend this theorem to the non-compact case and get the theorem that I wrote on the blackboard. Okay, thank you very much.